Okay. So we got this idea of junction overview, where with the skeleton being one pixel thick, we can basically just use this fairly easy convolution trick to figure out what type of junction everything is, or what's a junction, what's a terminal, and what's a connector. And so we can just use a convolution with a 3x3 neighborhood and keep the results, and that gives us our junction count. And then we can zoom into one sort of smaller part of the image to actually see, did it correctly do what we kind of intuitively thought it would do. And so now it shows all the points with sort of the label that they have, and that it seems to work fairly well. We end up having sort of multiple junction points here. So sort of we have 3 junction points that come in here. We have 3 different fibers that are coming together, but fundamentally we have kind of everything we need to have in the image. And so what we can show now is we can group it by sort of count, and so we can see the points that are 2 are just the terminals, so the ends of all of the network legs that we were looking at. The counts that are 3 is what most of the network is, and so these are sort of all the connectors between, and then the counts that are 4 are all of the junctions, and then the counts that are 5 are all sort of super junctions. But anything above 4 is basically in the same point, and we see that that point that's 5 falls right here, where we have all of these points kind of massed together. But that what 5 means is that when you look at the 3x3 neighborhood, that 5 of those pixels are filled up. And so ideally shouldn't have too many of those, but again, they do occasionally come up. And so now what we can do is something that one of the students just kind of asked about, is this idea of pruning. And so how do we go through this skeleton that we have and start to prune for the things that we're interested in. And so ideally, this is sort of model-based. This is where we know something about the structure that we're looking for, where we can say, you know, the branches we want to have need to have a minimum length. Otherwise, we shouldn't keep them at all. And then we can also incorporate sort of a minimum branch width. And so if we bring this together with the distance map, we now have the width at every point in the image and sort of its junction status. And so we can figure out how long a branch is and how wide it is by combining those 2 pieces of information. And so branch length is actually quite easy to filter for, because we just do a component labeling on the count 3 image, and that will give us all the branches, and they're all nicely separated because we've removed all of the junctions. And so we don't have any of the things that would have been connecting them together, and so we know they'll all get identified as separate components. And so we can go through here, and now we have sort of a segment ID for each one of these branches, and now we can see the segment length. We can also paint the image with the segment length sort of on top of it, where we can see, you know, the short segments appear in blue, which is a little hard to see on the projector, and the longer segments appear in red. But that basically, if we go in this image and we say we throw away everything that's less than 10, we get rid of a huge amount of the noise. And we can also start to overlay the ground truth as a way of kind of giving ourselves feedback of, did the pruning do the right things or not? And how does our skeleton look? And we see that we're actually quite close. We have a few issues we still need to kind of solve, but fundamentally we're getting closer and closer. And here, you know, obviously getting rid of these single dots, which represent the terminals of branches that are now deleted, we can do as well. But that's very easy to do, so it's not really a priority. What problems do you see with this skeleton right now? Yeah. Yeah. And why is that a big issue?
Well, like you said before, because we want to have streets, so we want to have a skeleton, and the skeleton is obviously connected, it cannot be disconnected.
Yeah. And so how would you fix it, or what could you do to fix it? Yeah.
The opposite of erosion, don't know what it's called.
Dilation?
Yes.
Yeah, so we can use dilation or distance maps to try to connect these little short segments together. We can also filter differently. So right now we just filtered on length, and so we got rid of really short streets. But if we filtered on width as well, then we could account for the fact that even though this is really short, it's still the same width as we'd expect a street to be, and so we keep it. And so that can kind of help us clean it. Yeah?
I think you said that all the lines were a single pixel width before.
They are,
So how would you filter on
with the distance map. So the distance map tells us how wide it was in the real object, right? So yeah, so all of these are a single pixel, and that's the only reason that the junction labeling works. But we know how far each pixel is away from the nearest boundary. And so we have sort of a width at each one of these points. And so here we can look at the segment maximum width, where we take the labeled images that we have and we take the value from the distance map, and that we can now show the maximum value for each segment and use that as a sort of additional criteria so that we don't have to throw away as many legs, and so that we can see the ones that are really short and really narrow, we can definitely throw away. And the ones that are sort of short and wider, we can keep. And so we can do sort of a much better job than we did before. So we now don't have that gap missing here, and we have that connected. But we've now gotten rid of sort of the end of this road. And if we look at the image, which is also always helpful to kind of go back to, that makes sense because you have sort of this tree on both sides going into the road, because you're looking at sort of on top, and often you have shadows and other structures that come in, but that make it hard to see how wide the road actually is. And so for our model, it didn't do anything wrong. That is, in the image, a narrower road than we would like to include. But because we're able to look at that and see very easily that these are two trees and they're just impinging on the road, it's not actually a narrower road, we're able to kind of make that distinction. But when you're sort of tweaking and debugging these things, it's quite helpful to kind of always look at all things, because it's not necessarily kind of the algorithm's fault for making some decisions. So now we could try to continue tweaking parameters, changing our image preprocessing, changing from value to saturation, changing our threshold to see if we could get that. But for the moment, we'll sort of keep this as is, as our sort of final result. You can take this yourself and go through the slides and tweak it and see if you can get a much better result. And there's actually problems where you can do that in more detail if you're interested. But now sort of one of the things that we can do, that we have this original structure, is sort of establish topology. And so now once we've cleaned up our graph much better, we can start to label everything as sort of endpoint, segment, junction, superjunction. So we just have one superjunction here and sort of plot that on top of the image. And so this is the same things we had before, just sort of displayed on top of the image and using colors a little bit better there. And so what this lets us do is we can start looking at the structure that we have and analyzing that in more detail. And so if we can take a graph out of the image, that makes our sort of life much simpler. And so looking at a topology like this on an image is quite nice to visualize, but it's quite hard to do any sort of reasonable processing with it. And so what we want to do here is kind of label everything uniquely. And so again, this is where component labeling works quite well, because if we label, if we have an image that looks like this, where we have sort of node, edge, We can take the nodes, label all those points the same, take the edges, label all the edge points the same, and now we have sort of a unique identifier for everything in our image, where we can now sort of grow out the nodes and the labels by one and see what things are actually connected together. And so we can do this quite easily and see that edge 1 connects sort of 1 and 3, edge 2 connects 2 and 3, edge 3 connects 3 and 4, edge 4 connects 3 and 6, and that basically we can get this sort of connectivity matrix where we have each node on here, and we can see which ones are connected together. And so the diagonal would be it connected with itself, which doesn't really mean anything for us. And so here we can now get sort of this fairly simple common graph representation of what a network looks like by keeping track of which things are connected to each other. And that we can again show the same way, where we have sort of all of the nodes and all of the edges connected that way. And once we have this sort of graph, rather than just an image, we can start to do more interesting analysis with it. So one of the more useful metrics you can do in material science is called tortuosity, where you look at sort of how direct is the segment that you're looking at. And so, if you think about kind of like, blood vessels or, your intestines connect sort of your stomach with your colon, and they have a distance, if you travel along them, of, meters, and the distance if you were to go directly would be a few centimeters. And so that would have a sort of very, very high tortuosity. And, analytical chemistry, it's quite important because if you're trying to kind of do certain types of chromatography, having high tortuosity makes a big difference. Vascular tissue, it can be a sign of pathology. So if you have blood vessels that aren't kind of growing directly to where they need to be. And similarly with road networks, if you're trying to figure out how long a journey will take, then tortuosity would let you know how kind of efficient the path you're taking would be. And so, if you had a helicopter, you could take the straight line, and if you have a car, you have to drive along the roads, and so you can have sort of a very tortuous paths. And so we can do that once we have the graph by now taking each one of the sort of pairs of edges that are connected, or pairs of nodes that are connected, and comparing the length along the graph, so the length in the number of sort of pixels that we have in the skeleton versus the Euclidean distance between them. And so that we can now show this. Is this not? Oh, here we show it by, I guess, transparency? Yeah, so we show it by transparency. I could also choose to show it by values. Okay, anyways. So in that example, we showed it by transparency, but you could also show it by width or some other metric where you're able to then see which values are more tortuous than other ones. Anyways, okay. It's because we do a second example down here. And, but then we can start to, I guess this one shows it as the tortuosity is different colors on the image. And so that we can start to show these images in sort of more graph-like ways, coloring sort of the more direct segments and the less direct segments, and then using sort of graph tools where we can have sort of a randomly organized graph and we can see all the different nodes and how they're connected together, kind of independent of the image space. So we can do things like graph analysis, where we have sort of fairly basic tools we can use, where we can look at like what's the degree of sort of each vertex. And so and what that tells us is, how many roads come out of every intersection. And so if you're trying to assess, how dangerous a city was for driving, three-way intersections are safer than four-way intersections and are much safer than like seven-way intersections. And so by looking at sort of the degree You could see the number of intersections that had a large number of roads coming into or out of them, and use that to kind of assess how dangerous or how safe it would be. So now to kind of go to another method that also sort of deals with topology quite a bit, is this idea of watershed. And so watershed is kind of a superpowered component labeling where you make sort of different, you use the shapes of the structures rather than just their connectivity in order to connect objects together and figure out which components are actually separated. And so we kind of remember from before that with like the distance map, if you look at this distance map, even though all these components are connected together, you intuitively see structures. So you see circles, you see gaps between them, you see objects, even though they weren't really there in the original segmentation, and even though they're kind of touching. That like the pattern is quite easy for us because they're sort of peaks that are present inside of this image, and if you look at sort of the peaks and the areas around it, it becomes quite easy to see. And so what watershed is really taking that intuition and trying to turn it into a useful technique. And so this is actually a technique that's quite viable. So in the data science competition 2018 from Kaggle, which we've had, I think, a few little examples from before, this was $100,000 you could win, and it was for segmenting cells in nuclei in cells. And so you had, all of these images like this, and you had to be able to go through it and identify where all the nuclei were. And so the technique that actually ended up winning was a sort of watershed-based technique for separating all of these different cells together. And so even in modern data science and big competitions where people have paid lots of money and using all kinds of really complicated machine learning algorithms and GPUs and everything else, they still incorporated watershed or the ideas from watershed in order to get a slightly better model. And so it wasn't just neurons that magically learn everything. There were also some kind of elements of image analysis that were brought into it. And so what they found was this sort of approach they used where they incorporated watershed and morphology, so kind of these erosion and dilation operations, in order to get the sort of best results. And of course, there's lots of terms here that you may not have ever seen before. Don't worry about those at all. It's just kind of the post-processing steps that we're interested in here, and it's just to show that these techniques are actually quite viable. It's not just random techniques you learn in a class. So we'll take sort of a simple example here from that competition where we have, it's from that competition, where we have these images that we load in, and we have the sort of colored image. We then have a grayscale representation, and then we have kind of a simple segmentation that we try to perform. And so the signal segmentation we show there is just using Otsu on the black and white image. So kind of what we covered in that automated technique. And then we have sort of rough component labeling based on what that was. So here, this is then what we should have found. So this shows us what we actually segmented using a fairly simple segmentation approach. And this shows what we should have segmented if our technique worked really well. And so the first thing we see is that there's, our threshold is too high, so we're missing out on objects. And then what we see is that we have objects that are quite messily next to each other. And so just because it's next to each other doesn't mean it's part of the same object. And so we'll need to have a fairly good way for separating the different objects from each other because there's a lot of them that sort of form right next to each other. And so if we kind of zoom into this, we can go down to kind of just one cell or one nuclei that we're looking at. We can see our segmentation value here. We can then look at sort of the labels where we see that, this is labeled as 1 and this is labeled as 2. And then we see the ground truth. And so the ground truth sort of shows us that this was label 37, this one was 39, and this one was 41. And so that we somehow need a technique for being able to take this and kind of draw a line in between it to get those separated well. And so Watershed, very similarly to this kind of ridge idea we just talked about, is again looking at the distance map as if it were sort of a topological map. And so that we have this here, the grayscale image that we can then segment, and that we can take and plot in sort of a 3D plot so that we see the values that are far away as being sort of quite negative, and the values that are sort of close being 0. And the idea with Watershed is that, like the name would kind of suggest, it's about sort of water flowing downhill. And so that we have our segmentation, we have our distance map, and then we have this idea of sort of local maxima. And so we go through all the points, and we see if it's kind of the largest point inside of its neighborhood, then we keep it, otherwise we don't. And so we end up going through the image and just keeping sort of these local maxima. So we have this 3 here, this 4 here, and this 7 up here. So there's no points that are higher than that. And so these are what we call sort of seeds. And that what we can do with Watershed is take all of these seeds and grow them. And now have sort of a segmentation from it. And so when we take our seeds that we found and grow them, we get this map here. And what we're trying to get is this. And so we're much closer. We've now separated these two objects, but we sort of still have this little tiny object in the middle. And we can now sort of remove elements that are too small and then regrow them again. And now we sort of have this breakdown that we wanted to have. So it's still not perfect. We're still missing this object. But since we didn't find it in our segmentation, we're not going to find it through thresholding. It's not going to add new sort of things we didn't have before to the image. It just sort of helps us split up the things that we already have. And so we can now take it and sort of apply it to the whole image and see that it worked, it worked really well in this case, but actually when we apply it to much larger images, it easily gets sort of confused. So that we have this problem that the images here the cells here get sort of split in half the wrong way. They get divided up into, 8 different chunks, even though it's just one object here. And so it's a bit too aggressive of a technique. And so it basically, by using kind of the shape and the local maxima, you can end up getting way too many objects in your image. And you sort of have to balance those two forces. And so with this, you could obviously set kind of a minimum sized object you want it to get. And if it's below a minimum, then you delete the objects and then you regrow it and you kind of do that iteratively. But it's still going to be quite tricky for objects like this, where they're just shaped very oddly. So now we can go to kind of one more example where we have this idea of looking at sort of batteries and sort of electrodes inside of them. And this is from a group at ETH. And all the data is made available publicly. And so you can sort of take these X-ray tomography images and look at sort of the micro and nano structures inside of them in order to kind of quantify how things are connected in the battery and the structures that you see. So here you sort of have this standard image of kind of a grayscale. We can perform sort of an Otsu threshold like we normally perform, and then sort of start to clean up our segmentation. We can then perform sort of a distance map on the image and start to perform kind of a labeling of what we're interested in seeing. And then we can perform Watershed on this to kind of break it up into different objects and show us all the boundaries for the objects and see that, for a number of them it worked quite well, but for a lot of them it started to add too many different boundaries and it split them in half perfectly. And so one of the things that you have to do here, like they did in the paper, is you'll find the objects that are sort of split in half perfectly and kind of manually recombine them together. And so if two things are next to each other and they're sharing a fairly large surface, then combine them together, otherwise leave them separate. We can also take this and start to represent it as a graph to kind of go to the more material science applications, where we can now see which of these nodes are actually connected together and what the connectivity of different nodes is inside the system. And so we can start to draw each one of these dots as a vertex, and then all the ones that are connected to each other as nodes. And so we see this one isn't connected to anything. These two are connected together because they're sort of split in half. That's what you'd expect. That graph isn't very meaningful. And that all of these three are kind of all touching. And so anything that was inside of them, or with batteries, of course, you're worried about like electron flows, then all of those would be able to conduct if they were connected to electricity. So when you're looking at this and you're trying to optimize it for conducting or optimize it for not conducting, having a graph representation of this is quite useful. And so here we can go and try to combine split electrodes by using some of the graph information that we have, and we're able to join a lot of them back together. And so it's not perfect, but we're able to get this one back, a number of the other ones, where this one simplified, this one simplified. And so using the graph combined with our information on the segments, we can get even more sort of tools to combine things back together. We can then sort of show the graph and start to quantify more things on it and see that on this graph we can start to label how many neighbors each one has and come up with more interesting analysis of our structures. And so here, that sort of degree plot that we had before, where we can see that there's a huge, or quite a few objects are not connected to anything or connected to only one or two things, but there's a few points where sort of 8 or more objects are connected together. And so if you were interested in making it conduct better, you'd probably want to have a shift sort of towards these higher number of connectivities. But if you wanted to connect it, have things connected less well, then you'd probably want to optimize for reducing this sort of mean degree metric. And sort of what this helps us do is have a single metric that we can work with in order to kind of improve the analysis that we're doing. And so it makes it a lot easier to sort of summarize our giant image into kind of one number by saying the average degree connectiveness of the nodes is this. And if you can reduce this, then you've made a better sample. And if you increase this, you've made a worse sample. And so that's sort of our main focus with that. So are there questions on this? So the exercises will go into this in slightly more detail. You can also go through the slides yourself and tweak some of the parameters and try to do a better job or change the analysis. Particularly for the road example, that was just sort of the simplest set of parameters. It's clearly possible to do a much, much, much better job at segmenting that road. I mean, that's something that Google does thousands of times a day, and so it must work fairly well. Or there must be techniques to do that much better than what we've just shown. That was just sort of the first introduction to that. So there's some other slides about distributions and analyzing multiple objects, but I think I'll put those off till next week so that we don't end up running too late. Or is class next week? Yeah.
Why not?
Well, the Easter holiday things move things around strangely.
We are not good.
Like on the 22nd of April.
Ah,
on
okay.
this Monday, and on the 25th or something is no lecture.
Ah, okay.
Something.
Yeah. I mean, it's on the course website. I think I have it there. So, okay. So if we go, I've also rearranged the website a little bit because I found it quite annoying that the exercises and the lectures were completely separated from one another, particularly because then you could have exercises that were associated with the wrong lecture or weeks that were wrong. And so now all the exercises and the lectures are in the same thing. So you basically have it organized by week. And so hopefully that should be easier and lead to fewer sort of confusion or problems. Oh yeah, it's the 25th that we don't have a lecture on. So for the complex objects one, yeah, it's again a lot of these examples that I've sort of shown before. There's some NIME exercises from sort of the old approaches. And then there's Kaggle notebooks for all of the newer ones, because a lot of those, like the battery data set, I think is 10 gigabytes or so. So it's quite large to download. And so you can do it on Kaggle without having to download anything locally. And yeah, we have the electron microscopy segmentation. We have street network. Where you can sort of see all the steps that we have on sort of a slightly different image and try to tweak the analysis and improve the results that you're able to get using kind of distance maps and thresholds and skeletonization. And so what's quite nice with that is that you can try your tests on a number of different images and then try to evaluate how well they worked. For the more advanced students, you can also try to figure out a good way of scoring how well you've extracted the topology. So with the segmentation problems, it's we have ROC curves. You can look at false positive rate, but for a topology, a false positive rate doesn't really make sense. And so if you look at this graph here, you could say by you missed those pixels, but you didn't really miss these pixels. It's just shifted a little bit. So coming up with a nice metric for optimizing roads is quite tricky to do, or optimizing graph extraction from images. And so trying to figure out how you would evaluate it and how you would sort of iterate and make your models work better and better is quite an interesting problem to work on. And so, yeah, there's plenty of opportunity to do things there. Okay. So if there's no questions, you can start on the exercises, or then just come up and ask me later.